Okay, good morning. This is our 16th lecture of the course Fluid Mechanics, and in the previous lecture, we have first analyzed the fundamental fluid motion, so which were translation, rotation, angular deformation, and the linear deformation. Okay, so out of which translation and rotation was completed. Now, next, our idea is to determine the rate of angular deformation or rate of shear strain. So, if you see in our original situation, this red colored outline was our actual fluid element, and after going through the rotation and deformation, it has gone through these change in angles delta alpha and delta beta, because of which its two adjoining faces have changed angle. So original angle was 90 degree and this angle is other than 90 degrees, so it means it has gone through some deformation also while it is rotating. Okay, so to quantify the rotation, we had already seen that if this is our original fluid element, then with reference to that, the changes in angle based on average rotation will be half of delta alpha minus delta beta. Okay, now if I see, so there may be representations of magnitudes wrongly in this figure, so please consider that into your mind. So this delta alpha angle should be larger than half of delta alpha minus delta beta, so representations may be wrong in terms of magnitude, but actual angle wise these are represented correctly. Okay, so now if delta alpha and delta beta are the total changes in angle, okay, what we have to do, we have to quantify the only contributions of deformation. Okay, so what will be the contribution of deformation? So contribution of deformation will be nothing but equal to total change minus change due to rotation. Okay, so that will be the contribution of rotation for each of the parallel, contribution of deformation for each of the parallel faces. Okay, so you will be finding that total was for the lower face, total angle was delta alpha minus rotation was half of delta alpha minus delta beta. So for the face, I can say sorry, this is O, this is A, and this is B. So for the face OA, my contribution of deformation is coming out to be, this will give me half of delta alpha plus delta beta. Okay. Now similarly, if I try to see for face B, so this is for face OA. Now what will be happening for face OB? For face OB, my total deformation was delta beta. Okay, and the part of rotation was half of delta alpha minus delta beta. Okay, so now if you see, you will be finding it minus of 1 by 2 delta alpha plus delta beta. So minus sign over here clearly showing that the deformation on face OB is actually taking place in clockwise direction. So I can also write it as nothing but 1 by 2 of delta alpha plus delta beta, but in which direction? Clockwise. Okay, whereas the previous one is in counterclockwise direction because it is the positive sign. Is this one clear? So from the total change, whenever we are actually taking out the component of rotation, then ultimately what we are getting is nothing but the contribution of the deformation. Okay, so if you want to see it schematically, so schematically you can see this red colored element in the third figure. This was nothing but at an angle of half of delta alpha minus delta beta. So from this point to this point angle was this. Okay, so now the total contribution after deformation is nothing but half of delta alpha plus delta beta. So whenever I'll be marking this angle, so this will be based on the rotated movement of the element. Okay, so now can you tell me then deformation we are trying to see over here in terms of the angle. So whenever we are having deformation in terms of the angle, that particular deformation is called as nothing but the angular deformation. Okay, so this I will be calling as, these two are nothing but the angular deformations. Okay, so if I have to find out the rate of, which one? OB delta, this will become minus minus plus, so it will be becoming,
so delta V plus delta V by 3 by 2 delta V.
okay, sorry, this was minus delta beta because it was in the clockwise direction. Okay. So angular deformation over here I have observed. Now after angular deformation, what is my next task? Because for fluids we have to quantify the rate of angular deformation. Okay, and rate of angular deformation is nothing but identical to that of the rate of shear strain. So I will be now quantifying rate of angular deformation, or in other way I can call it as nothing but the rate of shear strain. So that will be nothing but equal to how much? 1 by 2 delta alpha by delta t plus delta beta by delta. Fine. Now what are delta alpha by delta t and delta beta by delta t? These we have measured in the previous, we have quantified in the previous class. So what was delta alpha by delta t? Please tell me from the previous class. dV by dx, and delta beta by delta t was okay. So this is nothing but my rate of shear strain. Okay. So whenever I am defining this shear strain, so even either if you calculate on face OA or you calculate on face OB, in both the cases rate of shear strain is coming out to be same. Okay. So typically whenever we represent the shear strain, we use, or in general strain in fluid dynamics, we will be using the symbol epsilon. So epsilon we will use to represent shear strain, to represent strain in general. Okay. So can you tell me what is strain? Strain is a scalar, a vector, or a tensor? Scalar. It depends upon direction. In which direction strain is taking place. Okay. So one thing is very clear, that it is having direction. Apart from direction, does it depend upon any other parameter also? It also depends upon the face on which it is acting. Okay. So for example, if I fix over here the xy coordinate system, so I can say that whenever I am referring to the shear strain, then I can say that I am calculating shear strain on which plane? This is my plane. Let me, okay. So this is my plane, and then direction is also coming into picture. So it means I have to represent strain in the form of nothing but a tensor. So while representing the strain, I will be using this symbol epsilon x y. So meaning is I am calculating strain on x plane, and in which direction? Y direction. So first subscript represents the plane and second subscript represents the direction. Okay. So that is the reason whatever the rate of shear strain I have measured, I can represent it something like this: epsilon xy equal to half of del v by del x plus del u by del y. Now can you tell me if I have to, so this is epsilon xy on face OA. On face OB it will be, we are considering the y plane, so on face OB it is y plane and x direction. So for y plane x direction it is also coming out to be half of del v by del x plus del u by del y. So the meaning is that exy equal to e epsilon ys. Okay, so strains are nothing but symmetric. Fine, because for a fluid element to be in equilibrium, so if shear stress acting from all the sides is same, then in that case strains will be actually symmetric. Okay. Now likewise, if I wanted to calculate in xz and zx, can you calculate xz and zx? That will be simply half of del u by del z plus del w by del x. Similarly, if you want to calculate for the yz, because whenever I will be considering a three-dimensional fluid element, it will be having how many faces? 6 faces. So for all individual 6 faces, I can define this shear strain. Okay, now what next? Next is, we have talked about angular rotation, angular deformation, but one important part is still left, that is nothing but our linear deformation. Okay, so now let's try to quantify the rate of linear deformation. To quantify rate of linear deformation, what we will be doing? This was the fluid element O, A and B, and after some time, say it has become something like this. So O point has reached to O dash and A point has become A dash. Okay. So now whenever I will be quantifying this linear deformation, what I have to do? What will be linear deformation in this direction? Please tell me what will be linear deformation in this direction? O dash, A dash, that is the new length of the fluid element, minus the original length of the fluid element. So original length of the fluid element is OA. Is this point clear? O dash A dash minus OA. That will be my linear deformation. Okay. So we have to now quantify this. So how to quantify? OA was equal to delta x and say OB was equal to delta y. So these were the original sizes. Now if I have to determine the velocity, then say velocity in x direction at this point is u. Okay, what will be velocity at point A? Velocity at point A will be nothing but u plus del u by del x into delta x. Is this point clear? If I apply the Taylor series, only considering the first term of the Taylor series and neglecting the higher order terms, velocity at this point A will be u plus del u by del x into delta x. Okay. So now, if I say that in the original position of the fluid element and the new position of the fluid element, we have delta t as the time lag, then I can say that linear deformation will be, I can write linear deformation as nothing but First the total length. So total length is, what is the total length? O to O dash plus, or let me write it like this. What is, first tell me, what is O dash A dash? Can you quantify? We cannot. So what I will do, first I will write O to A. O to A is how much? Delta x. Then I will write A to A dash. How much is A to A dash? This is point A. This is point A dash. If point A is having this velocity and delta t time, then how much will be the distance A to A dash? Please tell me, velocity times time. So velocity is u plus del u by del x into delta x times delta. Okay. So now I have calculated O to A plus A to A dash. Okay. Now what I will do this calculation of O to O dash. So O to O dash I will be subtracting from this. So if I subtract O to O dash, can you tell me what is O to O dash? U delta t, U times delta t. Okay. So this is nothing but my, this complete expression is length O dash A. Is this point clear? And now if I am calculating deformation minus, I have to do OA. What is OA? Minus of delta x. Okay. So this is nothing but my linear deformation. So how much it is coming out? Please tell me. Delta x will cancel, u dt will cancel. So I will be getting nothing but del u by del x times delta x into delta. Fine? Because I have to calculate the deformation. So deformation will be nothing but new length of the element minus original. So original length is OA. So that is I have subtracted as delta. And O dash A dash, this complete term is nothing but O dash A dash. Is this one clear? Say this is your new length. This is your original length. So how much change in length is there in the fluid element? That is new length minus the original. Fine. Is it clear or still not clear? Not clear. Let us consider a solid bar. This is the original length. Now if I extend this bar, this is my new length. How much will be deformation? This much. Okay. Now if I am talking about a fluid element, then it will not be having only this deformation, but fluid element is also translating with the flow. So because of that, if it was at this point, now it has reached over here. So now new location is something like this. Okay. So new length is now O dash to A dash, and this was O to A was original length. So I have to calculate this O dash A dash minus OA. So to calculate O dash OS, first what we have done? First I have taken this distance OA, that is delta x. Then I have taken this distance from A point to A dash point. That is the velocity of point A is u plus del u by del x into delta x times delta t. So this distance. Now my total distance is this much, but I need to calculate only O dash A dash. So this much distance I have to subtract. So how much is this distance? Minus u delta t. So this is distance O dash A dash, and original length then is delta x. So this is my, is this clear now? Okay, so this is my now linear deformation. Now can you tell me what will be the linear strain over here? What will be linear strain? Deformation by original length. So del u by del x into delta x delta t by delta x. This is my linear strain. So this is once again a fixed quantity like for solids. Now we have to calculate the rate of linear strain. Okay. So rate of linear strain is that will be nothing but linear strain rate also. So I am writing that with epsilon x means it is acting on x plane and also acting in x direction. So that will be becoming equal to linear strain by delta t. Okay. So ultimately I will get epsilon xx as nothing but equal to how much? Epsilon xx by epsilon xx equal to delta u by. Okay. So velocity gradient of u component in x direction nothing but gives us the rate of linear strain. Okay. So similarly, if I have to calculate strain rate in y direction, then what it will be? Please tell me. Similarly, strain rate in y direction and y plane. Delta v by delta y. And strain rate in z, it will be delta w by delta z. Okay. So now if I have to write the total strain tensor, then how many components it will be having? We have three principal directions for a Cartesian coordinate system x, y, z. Okay. And number of element, this is the second order tensor. So number of element will be 3 square, which is equal to 9. Okay. So I will be finding that the total epsilon xx, epsilon xy, sorry, epsilon yx, zx, then xy, yy, zy, xz, yz and zz. Okay, fine. So this is my strain rate tensor. So inside this now you can substitute all the values. So what are the linear strains? Del u by del x, del v by del y and del w by del z. So my diagonals are frozen now. After diagonals, what I have? Shear, so which will be half of, this is xy, del v by del x plus del u by del y. Then here it will be half of del u by del z plus del w by del x. Fine. So like this you can fill out all the entries and ultimately you will be finding that this is a symmetric one. So whatever entries you are having in this direction, same will be entry over here. This entry and this entry will be same. So this is nothing but a symmetric strain tensor. Fine. Is this one clear? Now after strain, after linear strain, one more important term is which is called as volumetric strain. Okay. Or what will be volumetric strain? This is also sometimes called as bulk strain or volumetric dilatation. Okay, so these are the different names for this. Can you tell me what will be volumetric strain? Volumetric strain will be nothing but change in volume of the fluid element divided by its original volume and d by dt of that. Okay, so change in volume per unit volume is volumetric strain and rate of volumetric strain will be d by dt of del u by d. Fine. So if I say that I have a three-dimensional fluid element like this, size dx dy dz. Okay, and after some time in the flow field, this is at time t, after some time in the flow field, it has, I can write it as delta x, delta y, delta z, and after some time t plus delta t, it has actually changes in its size. So now this is delta x dash, delta y dash, and delta z dash. Okay. So if its dimensions are changing, then ultimately there will be change in its volume also. Okay. So what we have to find now, what are the new dimensions and then what are the changes. So how to calculate new dimensions? New dimensions simply we can calculate by using the analogy from the linear strain. So in linear strain, can you tell me what was the new dimension? New dimension in x direction was nothing but O dash, A dash, that was the new size of the element. So new size of the element I can write from here, it is nothing but new size of element delta x dash will be identical to O dash A dash, and what is O dash A dash from the previous discussion? Delta x plus u plus del u by del x into delta x times delta t minus u times delta t. So from here I can say that my new dimension is nothing but delta x plus del u by del x into delta x delta t, and ultimately I can take delta x common and it will be becoming 1 plus del u by del x into delta t. Is this one clear? So this is my new dimension of the fluid element delta x dash. Similarly, what will be the new dimensions delta y dash? Delta y times 1 plus del v by del y into delta t. And consider that while we are defining these new dimensions, we have considered Taylor series only up to the first series. So higher order terms we are neglecting by saying that if delta x, delta y and delta z are small, if these are small, then what will be their higher order terms? Delta x square these will be nothing but approaching to 0. Okay. So that is the reason we are neglecting the higher order terms of the Taylor series. Fine. Now what will be dimension in z direction? Delta z dash will be delta z times 1 plus del w by del z of delta t. Is this point clear? Anyone is having any doubt? So what will be new volume? Multiplication of all these three. So new volume is delta x, delta y, delta z times 1 plus del u by del x into delta t, 1 plus del v by del y into delta t times 1 plus del w by del z into delta t. Okay. So what will be change in volume? V new minus V original. Original volume was simply delta x, delta y, delta z. Okay. And also we will be having delta V by V, then delta x, delta y, delta z will be cancelling out. And ultimately if I calculate limit delta t approaches to 0, 1 by delta t of del v by v, then it comes out to be, I am not doing over here, this is just the algebraic manipulations of these equations. So if you do, finally you will be getting it as del u by del x plus del v by del y plus del w by del z. Is this one clear? So I have given you the new volume, you have the original volume, you try to do these mathematical manipulations. These are just simple algebraic manipulations. While you are doing so, any term which is becoming delta t square, that you can neglect. Okay, so out of this multiplication, all the terms having order delta t square or higher, these you can actually neglect. So by neglecting these terms, if you apply this limit, delta t approaches to 0. Why? Because we want to create d by dt situation, instantaneous rate of change of the fluid. So that if you do, you will be finding that it will be becoming del u by del x, del v by del y, and del w by del z. What is this quantity? Is this quantity gradient of velocity vector? This quantity is nothing but equal to the gradient of the velocity vector. Okay. So if this is gradient of velocity vector, then I can call it as nothing but in other words, continuity equation for incompressible flow. Okay. Okay, I will talk about that in later. But ultimately, whenever we will be finding that continuity equation for incompressible flow also comes out to be the same. Okay. So one important point we have seen over here, that the physical significance of gradient of a velocity vector is nothing but equal to the volumetric strain of the fluid, rate of volumetric strain of the fluid. Okay. So mathematically, if anywhere we find that gradient of velocity vector is given, physically we must infer from that it is nothing but the rate of volumetric strain of the fluid. Is this one clear? Please say something, either yes or no. Still you people are sleeping? 8 o'clock class. It seems like you are physically sitting but sleeping. Okay. So this is the rate of volumetric strain, which is coming out to be nothing but the divergence of velocity. Okay. Now next, we can talk about some other important parameters which are associated to this discussion of fluid kinematics, which are nothing but vorticity and circulation. Okay. So can anyone tell me what is vorticity? Have you heard of this term earlier? So vorticity is some quantity that helps us in defining the rotation of a fluid element. Okay. And it is simply equal to curl of velocity vector. Fine. A quantity which helps us in quantifying the rotation of a fluid medium or rotation of the flow, that is something which is called as the vorticity. Okay. And vorticity is simply equal to curl of velocity vector. Fine. So if you see, in yesterday's class I have defined the angular velocity vector, and angular velocity vector was nothing but half of curl of velocity vector. Okay. So similarly, if curl of velocity vector is coming out to be equal to vorticity, so I can define capital omega is the symbol which is popularly used for vorticity, but this is not the only symbol. So in different textbooks you will be finding different symbols people have used for it. Okay. So I am using over here capital omega. So this omega is nothing but equal to 2 times of small omega. Is this one clear? Now, with this definition, can you tell me what will be the formulation of omega vector? 2 times of rotation. So tell me, what was the rotation vector? del by del y of w minus del v by del z of I cap. Have I written it correctly? Plus j times, what will be next?
Del U by del Z.
Del u by del z minus del w by del x plus k cap
Del V by del X.
So this is my vorticity vector. Okay. Now what are the implications of the vorticity vector? The flow field for which vorticity vector is equal to 0 is called as irrotational flow. This is important one. Okay. So the flow field for which vorticity vector is equal to 0, that is simply called as a irrotational flow, and where vorticity vector is non-zero, that is called as rotational flow. Okay. Another important point is positive vorticity is nothing but represented as the counterclockwise rotation of the fluid, and negative vorticity will give clockwise rotation of the fluid. Is this point clear? So in any flow field, if I calculate the vorticity vector, and if the value of vorticity vector is actually 0, then I will be calling that particular flow is nothing but irrotational. And anywhere where my vorticity vector is equal to 0, that type of flow I will be calling as rotational. Okay, let me give you a simple example. A flow which is appearing to you that it is moving in a linear plane, that also can be rotational or irrotational. Okay, so for example, earlier also I have taken this example. If I consider that I have a solid wall and flow is happening over this solid wall, so whenever solid wall was not in contact, then my free stream velocity was u infinity. Okay, once I am coming close to the solid wall, then what will be happening? Velocity at this point will be 0, and whenever I am moving away from the wall, then velocity will keep on increasing, and at some point of time it will reach this value of the free stream velocity. So my velocity profile will be something like this. Okay. Similarly, if I keep on moving, the extent of velocity profile will keep on increasing. Something like this. Okay. So now, if I join the locus of all the points where my velocity has become 0.99 of u infinity, and if I draw a boundary to demarcate these points, then I get some layer over here, this particular region over here, where velocity is varying from 0 to 0.99 of u infinity. This particular region is called as boundary layer region. What this region is? This is called as boundary layer region. Okay, and outside the region we will be calling as outside boundary layer. Okay, so within boundary layer, if you see, the gradient of velocity is existing. So this is my u component of velocity, and this coordinate is y. So in within boundary layer, I can say I have the existence of del u by del y. Okay, so del u by del y over here is actually non-zero within this region, because whenever I am moving in the y direction, then value of velocity is changing within this boundary layer. Okay, on contrary, if I go to this region outside the boundary layer, then what is happening? All these velocity vectors are nothing but u infinity only. Okay, So if all the velocity vectors are u infinity, then by moving in y direction, value of velocity is not changing. So outside boundary layer, del u by del y will be 0. And if the flow is purely in x direction, then my v component of velocity inside as well as outside both will be 0. Is this one clear? Whatever I explained, is it clear or not? Okay. So now, if I define the vorticity vector within the boundary layer, so this is a flow in xy direction. So I will be getting nothing but which component of vorticity? Z component of vorticity. So Z component of vorticity is equal to del u by del y minus del v by del x. V is 0 for this flow field. So within the boundary layer, this is equal to del u by del y. And del u by del y within the boundary layer is non-zero. So it means it is having some non-zero value for boundary layer. What will happen outside boundary layer? Please tell me. Outside boundary layer, del u by del y is 0. So omega z will be equal to 0.
So why is the divided by 0?
Because you can see that this plate, when we bring close to the flow, effect of the plate is felt up to certain distance. After that, velocity becomes uniform. Okay, so that is the thing. So this line which I have drawn over here, this is the length up to which the effect of plate is felt. After that, the effect of plate is not felt. It means flow will keep on moving with its free stream conditions. So that's why velocity is not changing our force. Okay, is this one clear? So that is the reason, if velocity is not changing with y direction, then del u by del y is equal to 0. Okay, so now within boundary layer my vorticity is there, outside boundary layer vorticity is not there. So I can simply say that outside boundary layer my flow is what? Irrotational, and within the boundary layer flow is rotational. What is the physical implication of this? Can you tell me what is the physical implication of rotational and the irrotational flow? The physical implication is that if I consider a fluid particle over here, and this say this is just to mark its location, and if I consider a fluid particle over here, then in this portion, whatever the fluid particle I will be having, that will always be keeping its orientation same. It will not rotate. Okay, it will be always keeping its orientation fixed in the irrotational flow. But in case of rotational flow, I will be finding that while this fluid particle is moving within this flow field, at some point of time it may have this orientation, at some point of time it may have this orientation, at some point of time it may have this orientation. So what is happening to this fluid particle? So this fluid particle is actually keeping on rotating while it is flowing within the flow. Point is clear? Is this one clear or not? So any fluid particle which is in the irrotational flow, that will be only moving in straight line and it will not go to any rotation. If it is not going to any rotation, it will not have any angular deformation. On contrary, a fluid particle which is flowing over here, that will keep on rotating and it will go through the angular deformations and angular rotations. Fine. So another classification of this type of flow is, after this point there is no change in the velocity. So it means after this point my viscous effects are not significant. Okay, because only viscosity is responsible for change in velocity between the different layers of the fluid. So I can say that outside the boundary layer my flow is inviscid. So this is another nomenclature. Okay, and within the boundary layer flow is viscous. So here it is inviscid flow, here it is viscous flow. So from here, one important idea we are getting is that viscosity actually the cause of rotational. Okay, so anywhere if you are having viscosity which is causing the velocity gradient, that is the cause of rotational. Fine. If I have non-viscous situation, then of course gradients of the velocity will not exist, and if gradients are not existing, then ultimately our flow will be irrotational. Okay. Up to this point, is it clear? Now, let me consider a flow situation for which I have circular streamlines.
So actually we are next class in
Okay, I will just give this to, it's just a problem in a minute so that you can think on this. Okay. So this is one flow situation, and let us consider this is nothing but like a solid body rotation. This is a fluid element but like a solid body rotation. So the meaning of solid body rotation is this particular layer of fluid is moving with omega angular velocity. This is also moving with omega angular velocity. This is also moving with omega angular velocity. On the other hand, I have also another flow field. This is also circular only, but here this is not like a rigid body rotation. So here different fluid layers can have different angular velocities. Okay, or in other sense I can simply say that, say this is my cylindrical coordinate system. So this theta velocity u theta or v theta over here is actually r into omega, where omega is constant, and here I am saying that v theta is nothing but equal to some constant by r, and in both the cases velocity in radial direction is equal to 0. So vr is equal to 0, vr is equal to 0. So this is my r direction and this is my theta direction along the angle. You have to tell me out of these which one is rotational flow and which one is irrotational. Okay, so question is clear to all. So in both the cases, if you see streamlines are in circle. Okay, so from physical appearance it looks like both are nothing but rotational flows, but out of these one is rotational, one is irrotational. So you have to quantify vorticity vector for this and tell me the physical implications of this. Okay, so now we will stop at this.